So the next topic under our discussion in chemical bonding is the new topic, hybridization of molecules. When you go for hybridization, what do you mean by hybridization? The intermixing of atomic orbitals of same energy nearly same energy called degenerate nature means same energy to form equal number of new hybrid orbitals is simply called hybridization. I repeat, intermixing of atomic orbitals of the same sublevel of same energy which are degenerate in nature to form new individual identical hybridized orbitals. Equal number of new individual identical hybrid orbitals is simply called as hybridization. The hybridization in molecule, the type of hybridization in molecules the types of hybridization in molecules are, here you can take sp hybridization, sp2 hybridization, sp3 hybridization. But before going to the sp hybridization, sp2 hybridization and sp3 hybridization, one thing what you have to understand here is always the hybrid orbitals formed during hybridization, hybrid orbitals formed during hybridization, they always result in the formation of sigma bonds. Similarly, all the unhybridized atomic orbitals always results in the formation of pi bonds. Unhybridized atomic orbitals always results in the formation of pi bonds. In hybridization, the hybrid orbitals are formed due to valency electrons of only central atom in molecule. So here, if you go to the types of hybridizations, let us have a discussion about sp hybridization. If you go for sp hybridization examples, you can take beryllium chloride, you can take carbon dioxide, you can take in beryllium chloride, beryllium undergoes sp hybridization, in carbon dioxide, carbon undergoes sp hybridization. You can even take C2H2, acetylene, it's an organic hydrocarbon, acetylene. in acetylene carbon also undergoes sp hybridization. But here, first example, if we take beryllium chloride, let us have a discussion about the sp hybridization in the case of beryllium chloride. So if you take beryllium chloride, first you take beryllium chloride, molecule is beryllium chloride, this is beryllium chloride. In beryllium chloride, beryllium is the central atom. Take this beryllium, atomic number of beryllium is 4, so write the electronic configuration 1s2 2s2 1s2 2s2, and here if you take, this is the expanded electronic configuration of beryllium, so this is helium of 2s2. Helium of 2s2 is the nearest noble gas configuration. If it is nearest noble gas configuration, let us take this as ground state electronic configuration of beryllium. Now you have to convert this configuration from ground state to excited state configuration. So helium of 2s2 of 2px 2px0 2py0 2pz0 is still, we can write this as ground state electronic configuration only. Now you promote one of the electron from 2s atomic orbital of beryllium to 2px. If you are going to promote, then you get a new configuration, helium of 2s1 of 2px1 and 2py1 2py0 and 2pz0. This is the excited state configuration of beryllium. Because what is interesting is, when you are speaking about the hybridization, what are the atomic orbitals you are using for the hybridization? That atomic orbital must contain an unpaired electron. If the atomic orbital contains paired electron, then it is difficult for us, because the hybridization in beryllium chloride, we are confirming it as sp hybridization. If it is sp hybridization, then all the 4 electrons are filled up in the s orbital only. If you want to have sp hybridization to accommodate one new p orbital along with the s orbital in beryllium, one of the electron, if you promote from s orbital to p orbital, you find that one unpaired electron is there in the s orbital and one unpaired electron is there in the p orbital. So therefore here, take this 2s1 and 2p. So if you have a look at this unpaired electron of 2s atomic orbital and unpaired electron of 2px atomic orbital, because we are saying that in beryllium chloride, beryllium is undergoing sp hybridization, the atomic orbitals which are participating in the hybridization, they should have unpaired electrons to prepare hybrid orbitals. So we are taking one s atomic orbital with unpaired electron, I mean it is 2s atomic orbital, but the 2s atomic orbital, for our convenience, we can say it as simply s atomic orbital, which contain one unpaired electron, and 2px atomic orbital, simply we can say that it is p atomic orbital, again with one unpaired electron. That means the beryllium central atom in the beryllium chloride, it is having 2 pure atomic orbitals, one s atomic orbital and one p atomic orbital with 2 unpaired electrons. So therefore what is happening here is, so you know very well that the s atomic orbital is spherical in shape and the p atomic orbital is dumbbell in shape. From the shapes of atomic orbitals from the earlier topic, we can understand that the shape of s atomic orbital is spherical and the shape of p atomic orbital is dumbbell. So therefore here, when you are trying to prepare hybrid orbitals, the overlapping takes place. You take the s atomic orbital, of which is spherical in shape, it contains one electron, and it also has one p atomic orbital. P atomic orbital, it has one unpaired electron, and s atomic orbital, it has one electron. I'll take it like this, one cross I'll take and one dot I'm going to take. This dot represents the electron present in the s atomic orbital, which is spherical in shape, and p atomic orbital, which is dumbbell. Again it has one unpaired electron. So both these pure atomic orbitals participates in hybridization, participates in hybridization, and they result in the two hybrid orbitals, that is the mixing of the pure s atomic orbital of beryllium and the pure p atomic orbital of beryllium. The hybridization results in overlapping of atomic orbitals. Due to the overlapping of atomic orbitals in hybridization, we get two hybrid orbitals. One hybrid orbital contains one unpaired electron, another hybrid orbital also contains one unpaired electron. Both of them are having opposite spins. So here we have, this is one sp hybrid orbital and this is also one sp hybrid orbital, and this two sp hybrid orbitals, because they belong to beryllium, I have just make a note of beryllium like this. This is beryllium. So take this beryllium and take the beryllium, first sp hybrid orbital, take the second sp hybrid orbital which contain two unpaired electrons. So here this is, now if you take the two adjacent atoms of chlorine, in beryllium two adjacent atoms of chlorine are there. So therefore what I am going to do is take one chlorine, atomic number is 17. Here write the electronic configuration: neon of 3s2, 3px2, 3py2 and 3pz1. I am underlining this atomic orbital. If we count the total number of electrons in chlorine, atomic number is 17 electrons. Nearest noble gas configuration, neon contains 10 electrons. 10 plus 2 12, 12 plus 2 14, 14 plus 2 16, 16 plus 1 17. 17th electron of the chlorine is present in the 3pz atomic orbital, and this 3pz atomic orbital, I mean the p atomic orbital, 3p atomic orbital contains an unpaired electron. Because it contains an unpaired electron, it readily overlaps with the sp hybrid orbital of two sp hybrid orbitals of beryllium. So here I am noting one sp hybrid orbital of beryllium and here also sp hybrid orbital of beryllium, and take the two chlorines, one chlorine, this is chlorine, pure p atomic orbital, double shape. This pure p atomic orbital of chlorine, it contains one unpaired electron. That one unpaired electron is trying to make a bond formation. Because it is p orbital, so I am just noting down here as p atomic orbital, that is sp of p, sp hybrid orbital of beryllium and p atomic orbital of chlorine. The overlapping takes place and that will result in the formation of a sigma bond, because the sp hybrid orbital and the dumbbell shaped pure atomic orbital of chlorine, both of them, they are overlapping along the internuclear axis. When they are overlapping along the internuclear axis, the cloud which is formed is called sigma cloud. Similarly, the same kind of overlapping takes place for the remaining chlorine of beryllium chloride. That is, if you take again one more chlorine is there. So here the unpaired electron of p orbital of chlorine makes a bond formation, and this is chlorine p atomic orbital. So if it is p atomic orbital of chlorine, the overlapping takes place is again sigma bond overlapping. So here what we are noticing is beryllium, chlorine and chlorine, all of them, they are lying in the same plane. That is the reason we are getting two sigma bonds, and the overlapping taking place here between beryllium and the chlorine is sigma of sp of p, and here also the overlapping of the second chlorine with the central atom beryllium is sigma of sp of p. So therefore finally we can take the structure, that is covalent bond structure, as single bond, single bond. So therefore here the bond angle is 180 degrees and the shape of the molecule is linear shape. All three atoms are lying in the same plane, and with the bond angle between the two adjacent atoms with respect to the central atom beryllium is 180 degrees, and the beryllium undergoes sp